So just while people are filing in, I like to do this little poll. So raise your hand if you think that humans are intelligent. Come on. Everybody thinks humans are intelligent. Okay, now just bear with me. Raise your hand if you think chimpanzees are intelligent. This is like a central theme of my talk, so this is relevant. Dogs. Do you think dogs are intelligent? Okay, majority. Cats. Any cat people? Cats are intelligent. What about a mouse? Who thinks a mouse is intelligent? Okay. How about a parrot? More hands. How about a sparrow? Does it matter? Sparrow, parrot? Yeah, okay. How about a lizard, a chameleon, let's say? Still have some hands going up. How about a frog? A praying mantis. Who thinks a praying mantis is intelligent? We still have a few hands going up. Okay. How about a paramecium? Anyone think a paramecium intelligent? Does anyone think a tree is intelligent? There's always somebody. Okay, here we go. Okay. It's a good warm-up because I'm going to talk a lot about intelligence. We can sort of do the same thing with consciousness, but maybe not right now. I don't know if I'm going to get sound on this. It honestly doesn't really matter. So I should probably just soldier on. My name is Matt Taylor. I work for Numenta, which is a startup that's been around for like 12 years in Redwood City. I've worked there about 5 years. I'm the open source community manager. I've also been an engineer there. And I'm going to talk to you a lot about the brain and about how intelligence works in the brain and what we've done to try and replicate that in software. My agenda is to talk about intelligence, to define weak versus strong intelligence, and then dive into some minor brain science. We'll talk about different structures in the brain, like neurons, layers, and columns. And then I will introduce theories of intelligence that our company has worked on for years and years. We call it hierarchical temporal memory. I'll introduce a data format that we call sparse distributed representations. That's what SDRs are. You're not missing anything, anybody, so please come on in. I'm just giving you the agenda. And I'll talk about spatial pooling and temporal memory, which are intelligence algorithms, the way we understand that they work in the brain. And then I'll talk some about 3D object modeling and recognition and our discovery of a sensory motor circuit in the brain and try and explain to you how that works. So our mission at Numenta, am I good? Or should I be talking right now? Am I good to go? Okay, all right, just I didn't ask permission. Our mission at Numenta is to understand how intelligence works. And we have chosen the neocortex as our target to try and understand how it works because everybody's hand raised when I asked if humans were intelligent. And it's sort of what we're going for. Everybody agrees humans are intelligent. And that intelligence comes from the newest part of our brain, which is the neocortex. And then we want to create systems based upon those principles once we've done that research and we think we understand how it works. This was back in 2015. I saw this Wired article that said, AI has arrived. And I was like, huh. Somebody has a different definition of intelligence than I do, which is typical. And I do not like to poke deep learning or ANNs, but I do want to make a comparison between humans and the type of intelligent systems that we have today. A child that has never seen a dog before, for whatever reason, can be shown a dog about 5 times and then will indefinitely recognize dogs forever for the rest of his life. And any orientation, in any context, will know what a dog is. Whereas our state-of-the-art deep learning systems need to train over lots and lots of images. Now, there are some caveats to this. There are some ways that you can train things a little bit faster once you have a system that's already trained. But it does expose something that seems wrong. It seems this isn't really intelligent. So I call this weak AI, and just because I'm comparing it to strong AI, and you might, from science fiction, have an idea of what strong AI is. This is what Wikipedia says, that it requires the ability to reason and strategize and solve puzzles, make judgments when you're uncertain, represent knowledge and learn, and express common sense, plan, communicate in a common language. Now, all those things may be possible with different weak AI technologies that perhaps are focused on those specific endeavors. However, that last bullet is a huge bullet, integrating all of those skills towards common goals. That's taking your expert knowledge in one little niche area and being able to apply it to a lot of other places. And that's something that we don't have today. I posit that weak AI in its current form in artificial neural networks will not produce something that we would refer to as strong AI or artificial general intelligence or just intelligence in general. I don't like the term AI. I don't like artificial intelligence. There's nothing artificial about intelligence. It's either intelligent or it's not. So what's missing? If we're not going to get to strong AI from what we have today, what's missing? I'm going to show two things that I think is missing. One is realistic models of neurons. So the ANN point neuron that's at the core of pretty much every system that you work with today in deep learning and ANNs is a very simple neuron. It has very few synapses. It doesn't create new synapses over time. And it's just a basic sum input of its weights, and we learn by modifying those weights. Well, the pyramidal neuron in your brain does a whole lot more than that, and I'm going to go into some of what it does. The other thing that I think is missing is movement. Who can name something that's intelligent that doesn't move? Nobody ever does, because you can't. There's nothing that is intelligent on this earth that doesn't move. It feels like it's baked in. It's like an entity that needs to understand the world has to understand the boundary between itself and the world. And in order to test that boundary, you must interact with the world. You have to incorporate movement and behavior into the core of the system. When babies are born, what are they doing? They're moving all over randomly. They're learning and learning and learning like crazy. All of that random movement, our neurons firing and learning. When I do this, I feel that, and this and that. And then eventually, years and years later, they're playing baseball and all of that. This movement, we think, is totally essential to intelligence. I don't think you can have something that just sits and does nothing and you feed it data that can really be intelligent. And I'm going to talk about movement later, but first we have to talk about brains. So this is your brain. This is the neocortex, is the wrinkly part. I'm just not even going to talk about the old brain. If you spread this out, it's the size and proportion of a dinner napkin, okay, your neocortex, if you iron it out. And it's homogeneous throughout the entire structure. It looks the same. If you cut into it here versus here, you're going to find the same cellular structure, and it's based on this cortical column. And this is the structure that's repeated over and over and over, 200,000 times. It's like the size of a strand of spaghetti. And this cortical column is the key to intelligence in the cortex, because if we can figure out what this little processing unit is doing, we can figure out what makes us intelligent in our brains. So we've known for over 100 years that cortex, that sheet of cortex, has many different layers. This is Cajal. He was a neuroscientist back in the late 1800s. He drew lots of beautiful pictures of brains, including this one, which shows the different layers of cortex as he saw them in his microscope at the time. So we've always known these layers exist, and we've been trying to figure out what they do for years and years. Now, it's a more recent discovery that there are also columnar structures, like I just showed in that animation. So there's columns and there's layers. Each column has layers. In addition, those layers contain neurons, and those are really the atomic computing unit in your brain. So I'm going to talk quite a bit now about the pyramidal neuron. This is sort of what the pyramidal neuron looks like. It has these dendrites that span out to the sides and another apical dendrite that goes upwards. And there are different types of dendrites on this neuron. So I'm going to talk about proximal and distal dendrites and the difference and how it makes the cell behave. I'm not even going to talk about apical at this point, because I just don't have time. So proximal dendrites cause the cell to fire. That's what happens when they are stimulated. Each one of these little spindles on these dendrites, and proximal means close to the cell body. That's, if you saw earlier, those are the ones close, the red ones were far out, distal. These spindles are all synapses where other neurons have made connections to this neuron. So it's got proximal connections, and it's looking and seeing all those different neurons that are connected to it, whether it's firing or not. If we get some activity, and watch closely here, we get a little activity here and there, it increases the voltage of the cell locally. So all of these neurons, they try and maintain a consistent voltage. It's a little bit less than their surroundings. If they get stimulation through the synapses, that through some chemical processes increases the voltage because of ion pumps I am not a neuroscientist. I'm not going to get into the terms, but it increases the voltage locally, but not enough to do much if they're just sort of here and there and everywhere. The cell wants to dissipate that voltage. It's like a leaky pipe. It wants to equalize and be back to a normal voltage. However, if you get a lot of proximal stimulation through a lot of these synapses all at the same time, and then they all increase the voltage at once, then that can affect the voltage at the cell body. If the cell body voltage increases enough to breach a threshold, you get what's called an action potential. And that is a chain reaction that fires all the way down that cell's axon, and that indicates to any cell that it's connected to that it has fired and it is firing. This is like neuroscience 101. Now, so proximal stimulation, what's close to the cell, causes the cell to fire. The interesting thing here is, what about all these distal dendrites? What about all these distal connections? Well, for years, neuroscientists didn't know why they even existed, because they don't cause the cell to fire. No matter how much activity they get, they're too far away from the cell body to cause an action potential to ever occur. So what did they do? Well, again, it's similar to the proximal ones. If you get some activity in different parts of the dendritic tree, it's not enough to increase the voltage anywhere to make anything happen. But if you get a localized burst of activity on one of these dendrites, one of these segments, that causes something very similar to an action potential. We call this a dendritic spike. I hit the wrong button. There we go. A dendritic spike. If you want to look up the neuroscience, it's called an NMDA spike. This was discovered or reported by Matthew Larkham, who's a neuroscientist, I believe, in Europe. This distal stimulation sends that voltage pulse down the dendrite to the cell body, right? But it's still not enough to cause an action potential. So it still doesn't cause it to fire. But what it does do is raise the voltage at the cell body just enough that it affects its behavior for a certain period of time. We call it, it depolarizes the cell. It makes the cell predictive. It thinks that it's going to fire soon. So it's primed to fire. So when it does get that next proximal input, it's going to fire fast because it's almost to that threshold where it's going to fire. So this is core to our theory of intelligence, HTM theory, that these distal stimulation causes the cell to go into a predictive state. This predictive state of the cell, modeling this predictive state, is really important because what is your brain doing all the time? Your brain is a prediction engine. All you're trying to do is predict the thing that's going to happen next. Your brain's constantly predicting what happens next. You've always got cells in predictive state. You're always anticipating. Even looking at me, you know where my hands are going because you've seen people make these gestures. So having this predictive state is really crucial. So if these neurons have these different sort of integration zones, whereas if they get connections in this area, they are treated differently than versus another area, it goes forward that because they're all oriented in the same way and layers contain neurons, about 10,000 neurons, that those integration zones apply to the layer as well. This allows us to treat a layer of neurons much like a compute module that has different inputs. The proximal input is like the primary driver signal. Proximal input causes the cell to fire, right? But the distal input and the apical input can cause that cell to fire a little differently depending on the situation. What the distal information is contextual information, something about the state of the cell or the world at the time that proximal input was received. So these are more like modulatory signals. These are the ones that cause the cell to go into a predictive state and think it's going to fire next. I'm going to show you some software visualizations of a system running. I should have said this up front, but all of this theory is implemented in code, and the visualization I'm going to show you is code that I'm running and visualizing. When I show you something like this, it's a layer. It doesn't look like a cylinder, but it's a layer, and the different colors of each little block is a different state of a pyramidal neuron. So each cube is a pyramidal neuron. Okay, sparse distributed representations. It's always tricky for me to try and explain this. Imagine a fiber optics cable and imagine your spinal cord. This is the best way I think to do it. your brain gets information in the form of fiber optics transmissions for the most part. Okay, this is an analogy, but that space is constantly transmitting information, lots and lots and lots of times a second. And those are nerve axons, and those are neurons that are firing. That's information that's coming up your spinal cord to your brain. At any point in time, your brain's neurons are about 2% active. So that's a number we usually shoot for when we're trying to represent something in this data format. This is going to work better if I show you an example. So let me go and show you something about sparse distributed representations. So here's an example of a small sparse distributed representation. All it is a binary array. Okay, I've wrapped it around, but it could just be a one-dimensional binary array where a small percentage of them are on, 2% are on. The bits that are on mean something specific. It's not like ASCII. So the interesting thing about this is I've got this set, so there's 256 boxes, 5 of which are on right now. There are 8.8 billion ways to fit these 5 bits in this space. So it's a very big space to put data. And we typically use about 40 bits on, right. So here's really the capacity that we typically run with. And this is more atoms than there are in the known universe. So the point of this is the data structure, the data medium, the communications medium that your brain uses is never going to run out of space. It's never going to run out of ways to represent information, ever. So we're going to take advantage of that when we try and build our systems too. Another interesting graphics. Like I said, each one of these bits has some semantic meaning. Say you were trying to represent living things in this space for whatever reason. So the different bits might actually point to characteristics of living things and whether they exist on that living thing or not. This gives us some interesting things that we can do because we can do comparisons. Binary comparisons are really efficient. So here's an example of 2 just randomly generated SDRs, and on the right you can see where they overlap. This is a really important calculation that your brain does all the time. How closely does this input resemble what I've seen in the past? And so we can get an overlap score, which is a number that indicates how much they overlap, and you can tell semantically, specifically, what things overlap about that stuff. Unions are also really important, and this is just a binary OR. This represents the semantics of both of those SDRs. These are things that we use, that your brain uses all the time. So with these comparisons, you get some really interesting things that you can do. We have a partner called Cortical IO, and they have this API where if you give it a word, they'll give you back a bitmap or an SDR, a representation of that word where each bit has semantic meaning. If you ask it for the SDR for jaguar, well, that's an overloaded term. A jaguar could be a cat, it could be a car. I think there used to be a gaming system called a Jaguar. So it's overloaded, but you can help define better what you mean because you can do these calculations on SDRs. So you could say, oh, give me Jaguar, but also give me animal. And I'm just going to take all the animal bits out of the Jaguar representation. And what do I have left? Well, I'll send you their API, what I have left, to give me the most similar term, and it's car. So you can do this type of semantic calculation really nicely. And they're working on NLP applications using SDRs to represent information. Okay, so if SDRs are the information medium of the brain, how do we get data into that format? So we have to get data into some binary format so we can process it like the brain processes it. Biologically, our sensory organs are what do that. We're not in the business of replicating sensory organs. We're like focused on the cortex. So all the encoders that we create are very simple. So I'll give you, but they have the properties that we know are necessary for an encoding system. Like you have to encode similar inputs similarly. They have to semantically be similar. Dissimilar inputs also have to be dissimilar in the SDRs that we create when you encode them. Let me give you an example of a date-time encoder. This is a sense that you don't even have. This would be like if you had a clock embedded in your brain and you just knew exactly what time it was all the time. So here's a date. This is today. And I'm trying to encode like 4 different things about this timestamp. I'm going to encode what day of week it is, whether it's a weekend or not, the time of day and the season. And as I move forward, today to tomorrow, you can see the day of bits, the day of week bits change, the weekend bits change, and so the SDR, the semantic representation, is being maintained as we move through time. The season bits change as I go through February, March, April. If I go change the time bits change. And this encoding down here at the bottom, let me go back to my calendar. All we have to do is simply concatenate all of those representations together and feed it to the algorithm as its input space, and it knows the semantics of a date time, at least the ones that we've defined here. So this is a simple example. You can imagine maybe a scalar encoder. I'll just show you a scalar encoder. Here's a scalar encoder, and this is just 1 to 100. Periodically moving through the space. There's a lot of different ways you can code information. We're doing it very simply. I think that the encoding of information into this space is going to be just as big of a business as processing it, because every different area of expertise is going to want to encode their data a little bit differently, create your own sense, if you will. Okay, let's see where I'm at. Spatial pooling, I've got 20 more minutes. So I always debate whether I want to skip this or move through it, or push through it. There's structures in the brain called mini columns. In some of those layers, neurons are organized into mini columns. You actually see them here. I think this is in a mouse cortex. So we represent those in our model too. And what this does is these structures contribute to a process we call spatial pooling. And this is, if you imagine the input space that you're getting, that fiber optics cable that we want to process with our simulation of cortex, we can't be dependent upon that being nice and clean all the time. The world is noisy. So we want to translate that into another space where we have more control. And this is kind of what your brain is doing in a region of cortex. It's taking all that input it's seeing and it's translating it into another space, and we call them the space of mini columns. I'm going to show you a visualization of this so it's going to make more sense. But for right now, what I'll tell you is that each one of these mini columns has a receptive field to the input space, and they're all different. And those mini columns activate when enough bits in its receptive field turn on. So those things learn to recognize specific characteristics and features of that spatial input space over time. And we weight it, and we do Hebbian learning so that it starts, each mini column will start to hone in on certain specific features that it sort of has an affinity to throughout time. This is all about proximal feed-forward input, activating these mini columns. This helps us to normalize the sparsity, so no matter what sparsity the encoder is generating, we can normalize it and always turn 2% of those on. And it has to maintain the semantics of the input data, and it does. It does a good job at this. But this is all just talking about proximal input. These are this is a drawing, sort of a conceptual drawing of proximal connections to an input space getting feed-forward input and turning mini columns on. But there's also this interplay of distal connections too. So I told you the distal connections are the ones that are going to give us contextual information about really what's going to happen in that mini column. This is called the temporal memory part of the algorithm. Now, in your brain, these two things are happening simultaneously. We break them out into two different algorithms so that we can better understand what they're actually doing. So within the space of those active columns, I think it's time for me to turn the visualization on. Okay. This is a note sequencer, and I don't think the audio's on. Maybe you can hear it. It's okay. It's no big deal. The point is, I already plugged it in. It wasn't working. Oh, there's a volume? That changes everything. Okay. There we go. Nice. Thank you. Okay. That's a little too loud. All right. So what I have going on here is this is the input space. This would be like your fiber optics cable. And each one, this is really simple, by the way. Each one of these notes is being encoded as a different block of bits in that input space. I'll turn you down a little bit. What you see on the right, the big block, that's a layer of cells. We're sort of looking at it from the bottom or the top, however you want to say it. But if I move it like this, you can see those mini columns. Those are the mini columns that are being activated by that spatial input. And if we inspect this a little bit more closely, let me pause it. Okay, here's E, right? These mini columns are representing the spatial pattern E. If we move forward, these represent C sharp. And look, and maybe you can pay attention to the C sharp cells, mini columns, because when I loop back around, the same ones are active again. Okay, so this is just showing you how we've translated from the input space into the spatial pooler as a set of active mini columns. Now we have to learn a sequence memory of the spatial sequence over time. So one caveat before I talk about cell activity, like that, is that this sequence, this E to A sequence, I'm playing 4 notes, and then I'm resetting. I'm not looping. The algorithm doesn't see this as a loop of the same 4 things over and over and over and over and over, because that's a problem, because how do you tell when it ends? Is it 3 cycles? Is it 4? Is it 5? It's going to keep building segments, or it's going to keep growing synapses because it thinks that it's going to go on forever. So what we do is we'll play the 4 notes, and then we're basically going to tell it that's the end of the sequence. So every time it sees E, it sees it as if it was out of context. It's never seen an E, anything come before E, right? When it sees the C sharp, like this, it sees it within context because E came before it. So the temporal memory algorithm does 2 things. It decides which of these cells within the active columns are going to be active at this time step, and it decides which cells will go into a predictive state. And these sort of depend on each other. So there's 2 reasons that a cell within one of these mini columns would become active. One is if the column activates and there are no predictive cells at all. This is what happens when we get to E here, okay? In here, I'm going to turn on the predictive cells, and you can't see them because they're not there, because it can't predict nothing. It's seeing nothing, and all of a sudden an E comes. It can't predict that. So when that happens, the algorithm will turn on every cell in the mini column. This is called bursting. This is a neurological thing that happens in your brain. When you're expecting something to happen, and it doesn't happen, and something different happens, when those mini columns for that other different thing become activated, all the cells burst, because it's basically saying, I don't know what just happened. This could go in lots of different directions, right? So it's priming the sequence to go in many possible different directions. And I'll show you a better example of this in a moment. The other reason why it would turn cells on, okay, so I'm at C sharp right now. I'm going to show you the current cells that it is predicting will be active next, and I'll explain why in a moment. So we're at C sharp. If this is right, these must be the F sharp cells, right? It's predicting F sharp is next because you've seen it learn this several times over and over. And it should be, if we move forward, you'll see all of those F sharp cells, the blue ones, turn orange. Good. Thank God that worked. Okay. And then it goes on to predict the next one, which is going to be A. And so why is it doing that? Let's go back to C sharp. So it's doing that. These cells are predictive because, and I'm going to go grab one of them if I can. Whoops. There we go. So here's that cell that's in a predictive state right now. It's in a predictive state because it has all these distal connections to the last time steps cells that were on last time. It has learned that it follows whenever those cells turn on, it goes predictive. It thinks it's going to go next. That's why it's predictive. These distal dendrites that I told you cause the cell to become depolarized are depolarizing the cell because every time it's seen this in the past, it has fired next. So that is how it goes into a predictive state. What? No. There we go. Okay, so I'm gonna give you a little puzzle here. Let's let this run a little bit more. And then I think it's probably learned the sequence well enough. I'm gonna stop it right here. So let's turn on the predicted cells. What are these cells predicting? F sharp. What happens if it doesn't see an F sharp? What happens if we turn this off and let's play another E? You guys already said it. You're like on point. We're gonna see, instead of all those F sharp columns turn on, we're gonna see a bunch of E mini columns turn on, and it's gonna be confused. And because it's confused, it's gonna burst all the cells. Because it's just starting to learn E, C sharp, E. This is the first instance of E, C sharp, E it's ever seen. And I'm just gonna play it through. And you'll see that after it continues to burst for a while, because it doesn't know if is this a real thing, or if it just happens once, we're not gonna reinforce or build any segments to those previous neurons. But if we keep seeing it over and over and over, maybe we're not bursting anymore, right? We're predicting. Wow, but we're predicting a lot of cells, right? Why are we predicting so many things at this point? We used to be predicting about half this. Okay? We're making both predictions. It's predicting E, because it's just seen it a bunch of times, and it's predicting, what, F sharp, which it saw a bunch of times before. So you just saw it burst because it was confused and it didn't know the sequence, and then you saw me play it over and over, and then it nailed the sequence down, and now it knows both sequences. It knows the original sequence, and it knows that it could potentially branch at C sharp. The thing I want to drive home to you here, that this is a high-order sequence memory. The information in these cells, I'm at the very end of the sequence here, for A, these specific active cells represent A that followed E, that followed C sharp, that followed E. Does that make sense? So the information, the semantic information for every step in the sequence follows through with every step. Okay. So you just saw how the sequence memory uses its distal connections to loop back to itself, right? Well, when I showed this earlier, that distal information was coming from elsewhere. I didn't say where, but it was coming from elsewhere. What makes that temporal memory temporal is that its context is its past state. When it loops its distal dendrites back to other neurons within the same layer in that column, it's essentially linking to its past state. So when your context is your own state, the only thing that context can represent is your past. That's why it's a temporal sequence memory system. But, and yeah, this was the visualization I was supposed to show you for that. But what if it wasn't? And we can see different circuits in the cortical column where that distal information does not represent the temporal state of that layer. So for example, let's say that distal information represents a location on some object, okay? And now I gotta talk to you a little bit about location here. Let's just imagine a coffee cup in your brain. Imagine it over there on the floor, and imagine it floating in the air, and imagine it on the table in front of you, and imagine it in my hand, right? That coffee cup, you have a representation of that coffee cup that is not related to your position at all. It just exists in your brain. That's called an allocentric object model. An allocentric object or locations mean that's just related to itself. You can define a coffee cup in relation to itself and nothing else, right? That's what I'm talking about when I say a location on an object, not in relation to you where you are, but just in relation to the object itself. So if you know that you're touching an object, or you have a sensor that's getting feature information from an object at a certain place on the object, and we're getting proximal information that is the actual sensory data, like the sensation of the touch, or the retina information for the image that you're looking at, then you've got a way that you can identify objects over time as you sense them. So, and this is just another example of, say you have an entity and it's touching a thing and it touches it a bunch of times. Those locations that you're storing when you touch something new and you identify something new, those aren't relative to your body. Those aren't egocentric locations. Those are relative to the thing you're trying to understand, right? Okay. I'm going to swap to a totally different format, which I know throws people off, but this is a really good animation, okay? So imagine 2 layers. So this is the sensory motor circuit that we've discovered that we just put a paper out on. Imagine we have an input layer that is going to receive the location that we're about to touch something, the allocentric location on this coffee cup. It gets that as distal input. Because distal input, we know, depolarizes the cell, that's going to prime us for, that's going to be our prediction. Say, if we've ever touched something at that point on an object before, we might have some sensations that come up there. Once we do touch it and we get sensory information proximally, then we can say, okay, now I have a pair of data here. I've got a sensory feature at a location on an object. So that's what our first layer is going to do. It's just going to identify sensory features on objects, any objects that we touch here. The second layer, is going to receive that output, which is the active cells that are representing that sensation at that location, and it's going to do a pooling calculation. This layer is going to learn objects over time. It's going to retain and learn them. So assume we have trained this thing on a bunch of different objects, and we've had it touch a bunch of different things, and it knows them. So what this is going to represent, these bits in this output layer, is all the objects that it has felt something like that at something like that location, right? That could be a coffee cup, that could be a can of soda, that could be a ball. They all have similar sensory, tactile feelings at that point in the object. So now we're going to go touch it again. Here we get a different location, totally different feature. But since it's still the same object, we're gonna narrow down our representation of what this object is, because now we know, well, the ball does not feel like that at that location, right? So we can do this union operation, which is, if you remember, we're talking about SDRs, unions and comparisons. This is an SDR union operation to help narrow down what this object is that we're touching. You might imagine it in a black box and you're just trying to figure out what it is. That's what your brain's doing. When you touch something, it's like, that could be any number of 100 things. But then you touch it again and again. It's like, oh yeah, that's my cat Jimbo. And same thing, we're going back, having another touch, getting another sensory information, and then narrowing down once again, saying the coffee cup is the only object that I have in my database of objects that I've ever touched that this corresponds to. We can do this with multiple columns. So I've only talked about just one cortical column, right? That was that Vienna sausage looking thing that I talked about. Well, here's 3 of them working together. And in reality, you don't have a cortical column for each one of your fingers. We're just trying to simplify it, but it makes sense if you explain it this way, because they inform each other. And this is important. If we touch all 3 fingers at the same time, and all 3 of those columns that are very close to each other in your brain, let's say, get all of that information, they're all going to have a different idea of what it is, because these fingers have touched a lot of things, right, in a lot of different ways. So they're going to have an idea of what it is, and each one of those columns is going to say what they think. They're going to vote on what they think that thing might be, right? And they can inform each other, because the distal connections in that output layer, they go between columns. They actually share their distal information with other columns nearby. So they can inform other columns that say, I don't think that's a ball, by the way, and then it can update its model. And this all is happening just in one cortical column in its cooperation with other cortical columns without even introducing hierarchy into the equation. And show one more touch, and we can quickly identify that this is a cup. So when you have more sensation, and this makes intuitive sense, right? If you just go like this, I don't know what that is, I don't know, but if you go, you immediately know what the thing is that you're holding in your hand. Another reason why movement is important when you're building up a sensory motor model of the world, which is what we do, which is what intelligent things do. Okay. So, main thing here is that this whole cortical column, if we can we can figure this thing out, this is the key to intelligence in the neocortex, figuring out what this cortical column does. And we think we have a pretty good idea of what like 3 or 4 of these layers are doing. The thing I just showed you was the circuit between layer 2, 3, and layer 4. We think there's a very similar circuit between layer 5 and layer 6A that's doing another very similar process related to egocentric location. There's these things called what and where pathways. You can look it up if you're interested. But we're getting close to understand how this is working. So in summary, there's a lot going on in our neurons and in our brains that we're not modeling at all in today's ANN-based systems. Like I said, NMDA spikes that create that predictive state in the cell, and just the idea of movement or creating these types of circuits that enable learning from interaction with the world. So we got to have that interaction, and we have to have it baked in. So our theory proposes that model of intelligence. It's completely biologically constrained. We don't do anything in our code or in our research if we can't explain why based on sound neuroscience. And we try and incorporate these missing ingredients that I've been talking to you about. All of our stuff is very open. All of our code, all of our research code, all of our code that supports our papers are all on GitHub on the Numenta organization. I am the open source community manager, so if you want more information, you can contact me directly, matt@numenta.org. We publish all of our papers. The recent one is the theory of columns in the neocortex. That's what I was just trying to explain to you guys. We're really excited about this. We think that this is going to make a lot of interesting progress in AI. Numenta.org is our primary portal for me if you want to learn more about HTM. And also, I have a YouTube channel. So all of the visualizations and the stuff that I showed here, basically I took from that YouTube channel, and I keep producing more educational material about HTM. I even have an episode on bit arrays. So if you're hard up on educational material, search for HTM School on YouTube. So I'm open for questions. It's Friday and it's the last session, so shoot. Sir, yes. Yeah, that's a good point. Okay, yes, the example I gave about touching a cup, and I did a lot of examples with touching, that doesn't have to be touch. That can be other sensory modalities as well. If you think about the objects that you have represented in your brain right now, you don't just represent what they feel like, you represent what they look like, and sometimes what they sound like, and sometimes what they taste like. All of that is feature information that's related to an allocentric location on that object. So you know if you lick the top of the lollipop, it's going to taste different than if you lick the stick. So yes, yeah. You could, I'm sorry, you could have what? Buoys. Oh. Oh, sure, yeah, yeah. Right. Oh, we're going to have tons of different sensors. We're going to create new senses like crazy. It's easy to create new senses. I mean, I just showed you one that was like having a clock in your brain. It's easy to create new senses. The imagination is your limit, honestly.
Actually, just one quick announcement to make.
Sure, yes, go ahead.
So there's a networking event after the session, 6 to 9 in the atrium. And all are invited, so please don't leave before that.
That reminds me, we're having a meetup tonight at 7 at the Crown Plaza down the street. If you want to come learn more about HTM stuff. Sensory modalities, they're all treated similarly. Like I said, if you cut the cortex here versus here, it's the same algorithms that are happening. So, yes, you had a question. I just hard-coded it. We're talking about the note sequencer. Those encodings, I just said, okay, there's 4 notes and a rest, so I broke the space into 5 different sections and just turned on one of the sections for each one. But honestly, if I distributed it randomly for each, it would have been the same behavior. It doesn't necessarily matter how you encode it, as long as you semantically encode it. Like, I could have done something different and encoded A little bit closer to A sharp and A flat because they're closer in the chromatic scale. Is that the right word? They're closer in the scale. But I don't know if I want to do that. For the sake of this example, I just wanted to make it simple. Yes?
I think, again, I'm not sure if the question is directly related to the first part of the presentation. But I'm a student of complex systems, and I had a question about the interconnectivity of the brain and the neurons. Could you equate artificial intelligence to consciousness? And do you think that network systems can gain consciousness, artificial network systems can gain consciousness simply due to the sheer interconnectivity between different nodes? And will machine consciousness ever look anything like biological consciousness?
So I like to think about consciousness and intelligence, but I've come to the conclusion that if you go ask 10 different people what consciousness is, you get 10 different answers. So it's already hard to define what we're even talking about. I think there's a difference between intelligence and consciousness. What we're trying to do has nothing to do with consciousness. As far as we know, it has nothing to do with consciousness. We're just trying to figure out how intelligence works. Nobody knows how consciousness works. So it's hard to speculate about consciousness. I think you can have intelligent systems that don't necessarily need to be conscious. And perhaps you can have conscious systems that don't necessarily have intelligence. I'm not sure. So it's really hard to speculate. I don't think we're going to build conscious systems for quite a while. When we do, maybe this will contribute to those things. But there's a lot of very small things happening at sort of the synaptic level that we still don't quite understand. And we're trying to abstract from a functional standpoint what the neuron does, ignoring some of the synaptic details. But there could be a whole different oscillatory landscape going on at that synaptic level, and it's really hard to understand at this point. In the back, yeah. Yeah.
I was just wondering if you could discuss that the problem with visual pattern recognition is maybe the brain kind of understands what three dimensions are. So that's why maybe why you can show a kid a dog, and it's kind of like, but with the machine, seeing everything in two dimensions. So is that part of the problem about why you have to feed 10 million dogs to a machine?
Yeah.
Understand the concept that this is a 3D object?
Definitely. So there's a big difference. Three-dimensional space, your brain models three-dimensional space with neuron activations. You can't visualize how it's modeling that three-dimensional space because it's so abstract at that point. But yeah, when you think, okay, we're doing a lot of research about locations and about three-dimensional space right now. If you want to learn more about how this works in the brain, you can look up something called grid cells. There's some really interesting research that I can give you a quick and dirty, but if you have a mouse in a room and you can tell what neurons in its brain are firing, as it walks around the room, if you're just looking at one neuron that you think is a grid cell, it will fire at different parts of the room, and it will create a hexagonal grid of points because that neuron associates itself with specific different points in the room. And this actually scales up and down. So your brain is doing some crazy stuff to model three-dimensional space. And we're trying to figure out a lot about how that works right now. So I talked a lot about that allocentric location signal. I didn't tell you where it came from, right? We're working on where that comes from. How is that generated? We know that signal has to exist. For us to model 3D objects, that signal has to exist. And we're researching right now and writing more papers about how that is created. And if you want to learn more, come to the meetup tonight at 9, because one of our research engineers is talking about location and how it's treated in the brain. Yes, sir, in the back. Oh, right. So at any point in time, a model has a certain amount of predictive neurons. Those predictive neurons are predicting lots of things at the same time. So it could, if we're talking about a sequence, it may be predicting that you go this direction or that direction or that direction. All of those neurons could be active. And if one of those things actually happens, then that confirms that that's happening. So there is a probability distribution for future things in the future. I just glazed over all that. But you can get that information out of the system. Yes?
While at points when you stop giving proximal stimulation to this model, and it only still has distal things left, do your models dream?
No, I wouldn't categorize it like that, but I'll tell you something interesting. I told you that a cell can't fire without proximal input. Proximal input drives the cell to fire. That's not exactly true. Imagine yourself throwing a ball. All the neurons that are involved in you physically throwing a ball just fired in your brain, but they didn't get any proximal sensory information that confirmed that you were throwing that ball. That's because it was coming from the apical dendrites, because your imagination was unfolding that action down the hierarchy of your brain, and that was what was causing the cells to fire. So there's something to think about. Yes?
Are those proximal and distal inputs thought to be truly fundamentally different, or do they just, it does a function of the distance from the cell?
I don't know what you mean by truly fundamentally different. It's the same structure, I think. So typically, when you get to the first branch of the dendritic tree, you go from proximal to distal. That's about all I know about that. Where the neurons connect are coming from? Okay, here's the thing. A layer can't know anything about that, right? Because a layer, I didn't talk much about hierarchy, but these cortical columns are all part of a hierarchy, right? Just like in CNN and deep learning type stuff. There's a hierarchy going on in your brain. Lower levels are more granular things like edges and touches, and the higher level you get into abstract objects and then Bill Clinton, you know. Because you do have Bill Clinton neurons in your brain. That everybody's firing their Bill Clinton neurons right now. Okay, and I forgot the question. This always happens. No, honestly, what was I saying? Okay, sorry. Go ahead.
Well, first of all, congratulations.
Thanks.
You managed to foster more questions than the other presentation. Well done. Two questions, actually. The first is, did you say the meetup was at 7 or at 9?
7 till 9.
7 till 9.
Yeah, at the Crown Plaza, right down the street. It's 5. So I'll tell you exactly what it is. We've got this. I'm not giving this talk there. We have a talk from our community. He's going to talk about 3D modeling environments for training AI systems, which is relevant to the research that we're doing since we're doing 3D object recognition. Jeff Hawkins, our founder, is going to talk about this new paper that's called Why Columns Exist in the Neocortex. And so he'll go over some of the hard theory behind the last part of what I talked about here. And then we have a research engineer who's going to talk about how your brain represents location. And that's going to be an interesting talk. No. You don't need to go through HTM school. I mean, you might be a little lost here and there, but I would encourage you to come anyway. Yeah. Your second question. Yeah.
As was once said and is often repeated, all models are wrong. In some ways. So you've clearly gone farther than anyone else. Can you define for me what you think is useful in sentence? What are you shooting for? How far do you think you're going to need to go without accounting for chemical reactions that occur in and around these neurons? Do you have to go there?
I ask myself this question quite a bit. The thing is, you have to go back to the mission of our company. Where did it go? There it is. Understand how intelligence works in the neocortex. Create systems based upon those principles. We're not focused on productizing or necessarily finding anything useful to do with this. We believe that this mission itself will be valuable no matter what. If we can understand how intelligence works, it will present its value at some point in the future. That being said, we do have some sample applications that we've tried to build just to test out and see what we could do with this thing as we sort of go along. A lot of anomaly detection applications, because we seem to do pretty well at temporal anomaly detection, and that's something that we can say, well, ANNs aren't great at this, but we can do sort of good at it. But it's still, we're not trying to compete. We can't do spatial image classification the way that GANs can do it at all. It's a completely different mechanism. But there's nothing temporal about that image classification, right? If you think about how you look at images, you're doing it temporally. You're scanning the room with your eyes all the time, even though you don't even know it. You're saccading all around. That's contributing to your model of everything that you're looking at. So that time element is baked into everything that your brain does.
It's really four-dimensional, three-spatial in one.
Yeah. And if you think about SDRs, I mean, those are high-dimensional spaces, super high-dimensional spaces. So all the attributes of high-dimensional spaces that you hear even Jeff Hinton talk about when he talks about capsules, we've already been playing with that for years. Okay. Grok is a partner of ours. They're a company that has licensed our technology, and they have an IT analytics platform that runs our code, like our open source code under the hood.
And so is that commercially a viable thing? I mean, is that out there doing
Yeah.
detection with credit cards?
No, they're not doing fraud detection. They're like helping DevOps people identify when servers are having problems. So they hook into CloudWatch. They get all the information from all the AWS servers, the CPUs and the network in and out and the read writes and all that stuff, and automatically creates models, HTML models for each one of those things, and just does anomaly detection. So the longer it sees those models over time, the smarter it gets about them. You never have to refresh the models. Even if major patterns change, it will adjust over time. It'll throw anomalies, and then it'll forget about them eventually, just like you do when something becomes the new normal.
So is Amazon actually using that? I mean, that's
No.
just experimental.
Well, no, they offer a product on the Amazon platform. Grok does, Grok the company. And I think the product is called Grok as well. Okay, yeah, in the back.
Yeah, to what degree have you found system states that are analogous to human disease or lesion sorts of states? I have to imagine you found things where like it's hallucinating, it has
Oh, sure. Yeah. Well, so we have some papers actually that will simulate not lesions but failure of certain percentage of neurons in the system, and it still performs surprisingly well. Sort of the same way that your brain does. It's really redundant. Your brain's extremely redundant. I mean you kill neurons every time you drink a beer. So yeah.
So what happens if you have two proximals firing off at the same time? So for example, them touching cold water and then someone touching hot water.
Well,
One is hot, but it's relatively
so you have to remember these are whole different sets of neurons and whole different cortical columns that are being if you've got one hand over here touching hot, one touching cold. But I don't know. I used to go to this place in St. Louis as a kid called the Magic House, and they had these alternating coils with hot and cold water inside them. And if you touched them and touched them all at the same time, it felt burning hot. And you're like, ah. That's like an optical illusion for your senses. So your brain is still susceptible to hacks and attacks. Maybe not so bad as like ANN systems are today, but you are susceptible to optical illusions and sensory illusions. But that is